Hi, thank you for attending this conference. And my name is Michael Chen. I'm one of the engineering manager here at Meta for AI infrastructure. I will be host the Q&A session for the morning talks. Sujoy couldn't join us for this Q&A session, but he will join the afternoon Q&A session. First of all, I would like to have the speakers to do a brief self-introduction of themselves. KV, you want to go ahead?
Hi, my name is Kaushik Veeraraghavan. I'm a software engineer at Meta. I work on various problems in the AI domain.
Thank you, KV. Savin?
Hi, my name is Savin. I'm a co-founder and CTO at Bounds. I've spent my entire career building ML infrastructure. Previously, I was at Netflix. Prior to that, I built similar systems at LinkedIn. Excited to be here.
Thank you, Savin. Ketan?
Hello, everyone. My name is Ketan. I am the CEO and co-founder at Union. Prior to this, I was at Lyft. I used to lead the machine learning platform at Lyft. And rest of my career is across various types of storage and infrastructure domain and mapping. I'm really excited to be here. Thank you.
Thank you, Ketan. Next, we have Susan.
Hey, everyone. My name is Susan. I'm a research engineer at Meta AI, working on developing large language models.
Thank you, Susan. And Alexander.
Hi, everyone. I'm Alexander. I'm senior staff engineer at Cruise ML Infrastructure. And before that, I worked in Facebook AI, and I have a decade of experience building a infrastructure.
Cool. Thank you. Thank you for all the introductions. So we obviously at Scale, we talk about all the different challenges at Scale. So I was wondering, can a couple of you guys potentially talk about what does Scale mean to you, and why is it important for the company to think about Scale so early on?
I guess I can go. Yeah,
go for it. Go for it, Savin.
Yeah.
Sure. Yeah. I mean, when we talk about Scale for a machine learning project, I guess it's easy to sort of like see that data and compute, those are kind of like the foundational components. So the two sort of like natural dimension for any kind of machine learning project could be along those axes. Are you processing, like what volume of data are you processing? What kind of compute needs that you have? But then it's also important to sort of like step back a little bit from the definition of a singular ML project and look at it from the lens of an organization. There are like few other dimensions that may sort of like, start to emerge. One is, of course, sort of like this notion of volume. How many projects are you running concurrently? Are you running multiple experiments, multiple A/B tests? You have similar pipelines training multiple different variations of the same model and whatnot. So that's a very, very important part of the Scale process. Yet another dimension could very well be around the variety of use cases. You can have sort of like organizations who have, let's say, a couple of tentpole use cases for machine learning. So at Netflix, our tentpole examples were recommendations for the end user, as well as figuring out what content Netflix should be buying and how it should be constructing its portfolio of content over a period of time. And these two problems are very different. And then, of course, there are sort of like many other problems in between as well. So depending on sort of like how an organization is investing in machine learning, they would sort of like be on one end or like at some place on the variety spectrum. And then yet another aspect could be around velocity, pretty much, right? Like what is the time to market for a model? How quickly do you want to get a model live and kicking in production? And it's important for organizations to really sort of like understand all of these different facets when they are thinking about building infrastructure of any shape and size, whether it's adopting an open source solution, building something in-house, buying a commercial platform. And I think what I have seen in my past experience and now working with many major enterprises as well, it's usually important to have a rough inkling of what the future entails. Of course, nobody can predict what value machine learning is going to provide to the business. It's very exploratory at the very beginning. And it's important it's ideal if the infrastructure can scale with the company's needs. And that's been sort of like our focus all throughout at Netflix and now at Bounds, how do we sort of like build infrastructure that scales with our customers' needs across all of these dimensions?
Great, thank you, Savin. Anyone else?
Yeah, let me add a little bit to what Savin said. Actually, Savin covered most of the very important points. I think data. We all know data, compute, and the type of variety of infrastructure that has to scale. Also, organization scale, right? They start small, scale quickly, and within a blink of an eye, you're like, oh, you have 200 data scientists in the company, and so and for me, that is a very interesting aspect of scale as well. Another interesting aspect of scale that I've been also seeing with a lot of companies, and this is actually the natural progression of any software product or even an ML product, is essentially you should start simple and then you kind of scale up. But when you scale in this way, your needs drastically change and vary. And so the system and the infrastructure needs to scale with that. And so I think most of the other things probably Savin covered really well. So those are my aspects of scale, and I completely concur with Savin. I think one thing I'll bring up is like sometimes when we are solving really crazy problems. So I was at Lyft where we had all kinds of different problems. What ends up happening is the access to scale is also limited across different teams within a company. Like some teams actually are just one engineer and two engineers, and the ROI is not directly attributable to the solution potentially that they're proposing. While there is a team that has a directly attributable ROI, and then they're like, you can put 20 people on that, and you can get all the GPUs in the world, and for you guys, you don't get anything. And so I think at scale, a company needs to take care that you can access almost everything across the company. So these are that's why I think it's important to think about these variety of dimensions and scale. And organizations probably can benefit the most and actually leverage scale with much better within the organization to get the most.
Definitely, we want to leverage scale to in the organization for sure. Thank you, Ketan, for that. Next, I guess as we grow in the AI system scale, what are the things to watch that will break next? I mean, obviously there will be things to break, but I mean, if you guys can share your opinions, it will be great for us to watch out ahead of time, right? Anyone?
Maybe I can share some thoughts. So it's a great question. And one scalability bottleneck I would like to mention is about reliability and maintenance. As we grow as systems, we could expect various kind of failures to happen, and they, in many cases, require engineering attention. So what can we do to scale our ability to respond to those failures and to debug those failures efficiently? One trend I have seen is that people now care more about reliability and debugability of the end-to-end ML pipelines rather than individual stages, such as data process or trainer. And at Cruise, we introduced a concept of customer perceived reliability that tries to allude to what actually our users feel compared to like individual infra teams thinking what is their reliability rate. And we actually noticed them tending to be drastically different. That was such a revelation. So I think first step in actually solving this bottleneck is speaking common language between users of the system and infrastructure suppliers. And for those who watched my talk, I introduced the concept of one platform we have at Cruise. This is a system where we define standard interfaces for all the stages in typical machine learning pipeline, such as data processor, trainer, error miner, and so on. And now think from this perspective, like if you really want your system to be reliable and easy to debug, you want to very easily attribute which stages of pipeline are contributing to your reliability problems. And maybe individual teams owning those stages, they also want to understand which versions of their releases, let's say, or flavors of their systems are contributing to problems. So this is sort of hierarchical reliability data frame. And one way to kind of make it easy to consume by all the different personas interested in reliability can be something like icicle chart. I personally found very useful, but there could be other ways to represent reliability. And there are like many other aspects that enable you to have reliable and scalable end-to-end ML pipelines, such as standardized retries, standardized log syncs, error propagations through all these stages. So I would say the main bottleneck is fragmentation. Like if you don't solve fragmentation, then you can't really have those standard layers for unified experience debugging and attributing errors in your ML pipelines. If you address fragmentation, then you're actually in a much better position. So I would encourage people to proactively think about how their pipelines will grow and change over time, and how you can prevent fragmentation from growing so large that it's just impossible to solve.
Great point. Thank you, Alexander. Anybody else?
I guess I'll chip in again here. So we are at the AI infrastructure conference here at Scale. So infrastructure will be a bottleneck for most companies. You know, not everybody has access to the best infrastructure out there. Right in the early parts with AWS and GCP and so on, it's becoming easier, but it's still not. It's not still attainable. So that will be a bottleneck, and we have seen that consistently across when you're working with many different people. And the infrastructure may also be in terms of type of thing that you want to do. Do you want to do Spark, or use Ray, or use GPUs, or use like some MPI type of trading? And not everybody has actually tried to run this at scale. And so when you are working with a new problem, and this was actually 7 or 8 years ago, my team was the first team to actually start using Spark at Lyft, and we were like, oh my God, to productionize this, to run every 10 minutes, this is going to be a whole nightmare. And that took like 6 months. By that 6 months, the ROI of the proposed model was already depreciated. There was a new model in development which needed GPUs. I was like, oh my God, now it's like a new thing. So you see, it's not just infrastructure; it's the changing business and the infrastructure that matches the business need. Another thing is I'll give another example within a team that I worked in, is that when you're new and you have the new problem and you attack it with machine learning, it's amazing. You get like very quick wins. You throw an XGBoost model and you do some modeling and you have a win. And then the second one, now you're like, okay, let's improve this further. That's where it starts becoming challenging. And we see that the ROI kind of like depreciates. It's a huge potential churn. It causes churn, people leave. It's a lot of problem that happens. So that will be a bottleneck if you don't plan out what exactly is it that you want to achieve as a business from doing this over a period. And it's not like, and I've seen this is the other problem that we actually tend to think that, oh, there's one problem, let's send a data scientist there, ship him in, solve the problem, take him out and put him somewhere else. That's not how it works. It is a product. You have to constantly keep on working on it and accept that sometimes the same technique that you used yesterday will not work today. So I think these are some of the things. I've also seen problems when, like, in my talk, I touched a little bit on boilerplate code. Like people see problems that the value generation is slowing down. They're adding more engineers and more data scientists, but actually doesn't really improve value generation. Yeah, there's a marginal improvement, but essentially it turns out that you're probably not working on the most important part of your problem. And like, I'll give you an example. One of the users of our open source product migrated, and they saw that after migrating, they deleted 66%. Another one saw 95% code deletion. And I was like, okay, what was that 95%? I decided to look up the code. I'm like, this has nothing to do with the problem. You're just like writing all kinds of things. And these are products that exist out there, right? And so is this a bottleneck? It's very easy to see it in hindsight. When you're doing it, it doesn't seem like a bottleneck. It's like, oh, I need to solve my problem. I'm going to do this. I'm going to do that. So, looking around, taking a step back sometimes and seeing what's out there and who has solved what kind of problems might help. So those are a few things that I've observed.
Great. Thank you, Ketan, for that answer. Next, we have a few talk-specific questions. So I will ask the different speakers. So first of all, KV, Kaushik, you have a question from audience related to the question reads as currently most profitable application of ML is ads. Will that always be the case in 5, 10, 20 years from now? What other AI machine learning use case can you foresee eventually overtake ads as a potential revenue stream?
Thanks for asking that question, whoever asked it, and thanks, Michael, for relaying it on. This is a super interesting question, and I'll refer to something I shared at the end of my talk. As we're all aware, this whole field of AI is constantly evolving. And if you go back and look at computer science overall, a bunch of the interesting ideas in AI and so on that we're now exploiting actually came about in the 70s. What changed recently is two interesting things. One, the prevalence of data. And second, we started getting better hardware and started having better software systems, especially distributed systems and such, that could leverage all that data and leverage the algorithms and the strategies that were developed in the 70s to start exploiting them. And we can now see some really interesting things, like many of us are used to, on our phones using the combination of, like Siri or Hello Google or Alexa or these things to like have an AI system that responds to our needs. Or if you think about some of the things that Susan shared, she shared about OPT3 and she shared about some of these interesting language models, really large language models that are coming about. Some of you might have also used things like DALL-E, right? You can get cat photos on the internet by just like writing a sentence to a computer and it gives you this amazing image back. So the way that I think about this problem is ads currently happens to be the avenue for us to fully leverage AI, and we have a practical business use case that we can apply all these AI strategies to. So obviously it's generating a bunch of revenue for us. But if we go beyond that, and we look at truly the technology and the options or the doors that AI opens, there's a whole bunch of amazing things that it can do, right? We spoke about language translation. Some of you might be listening with closed caption enabled. So if there's an AI system that's translating from me speaking, I speak pretty fast, I sometimes slur, right? If you can have AI systems that automatically capture what I'm saying and translate this into text, that's kind of amazing. And then I want to recount a personal experience. A couple of weekends ago, we were on a long road trip down to the Western Washington coast, and we were, just talking, me, my kid, when we were with our family. And I was describing to him how we now have cars that can be self-driving. And he didn't understand what this was, right? Because you could see his parents spending hours driving our car from home to the beach. And he was just wondering, how is this possible that a car drives itself? So the reason I'm bringing up this anecdote is that AI is dramatically evolving. In the past few years, we've seen some fantastic things happen. And now we're accelerating towards this path where we see AI, enabling self-driving cars, possibly all these amazing things with language understanding, content understanding, and such. So yes, ranking, recommendations, and all the ads-related things are the things that we understand now. But as the technology and space evolves, I'm sure we're going to come up with a bunch of interesting applications that can leverage this and we can possibly monetize. So I think that there's many, many opportunities up in front. And for all of us who are thinking about these systems, scale, and so on, we should think about how to accelerate the growth and the adoption of this technology, because that might open all sorts of new and interesting doors. So yes, I totally feel like in 10, 15 years, we're going to be looking at very different revenue models, possibly different sets of applications and use cases that are very different from today. I don't have a crystal ball or something to describe the transition from today to ads to the future, but I'm excited about the possibilities that the future brings.
Great. Thank you, KV. We do have another question for you related to fault tolerance. So fault tolerance in machine learning come at additional costs, such as data replication, checkpoint migration, which are increased, kind of expensive, right? So what are your thoughts about the cost aspect for the AI inference system?
I think it's a really, this is another really good question, so thanks to whoever posed this. The way that I think about this problem is the following. We heard just today, right? We had Alexander, Ketan, and others share a little bit about reliability, fault tolerance, and infrastructure components. And then earlier to that, we had Savin share a little bit about like how we want to scale systems. So if I put my like traditional infrastructure engineering hat on, the way I think about this is the whole notion of fault tolerance and reliability has existed for a long period of time. In fact, there's this conference, like this set of conferences around fault tolerance and so on that have existed for like 30 or 40 years. Distributed computing has existed for a long time. So as engineers, or especially as system builders, we always think about failure. What could happen, let's say, to my individual machine? Could individual components like my hard drive die? Or maybe there's like errors in DIM. This is why we do things like error correcting codes. And then when you think of multiple machines that hold, let's say, data for storage systems, lots of people in industry and academia have invented things like Reed-Solomon encoding. So you take a bunch of data, you stripe it across many different machines, you allow sensitive machines to fail, but you can read all the data back, right? Similarly, when you have large-scale systems, we always think of failure modes where we say things like, oh, this entire machine loses power. Maybe, Alexander mentioned this notion of maintenance. What happens if there's physical maintenance that takes down a fraction of my data center, or maybe a network outage that takes down an entire data center or a region offline? So we always think about failures at all these different scales. And traditionally, we always think about compute systems and how we could possibly replicate load or replicate requests. And then the stateful systems in the backend, like databases and storage, how we would have writes happening to multiple different locations, or maybe you have a caching layer that translates data around. So these principles for thinking about how to build systems and the type of failures that we have always existed. And there's always a cost to it. So the way that I think about AI now is AI is just the newest use case that is running on top of all our systems and leveraging our hardware and compute systems in a very different way for a different set of workloads, right? So these problems have always existed. And honestly, many of us here in this call, and I'm sure a large fraction of the audience, have always thought about failure and certain other things. So yes, obviously we'll have this failure. We have to replicate checkpoints around. We have to distribute computation around. But the interesting thing here is not necessarily the cost of it from a per se perspective, but it's how do you optimize it, or how do you have this workload adapt to it? So in the case of AI, one interesting takeaway is if you want to take your training job and run it, from a failed region and you want to move it to some other region, you have to get enough capacity to recreate that entire gang job. And then you have to make sure that every machine that gets resumed has all the state that's needed for us to be able to kick the job off. So the interesting things are in the software abstractions that are above the storage layer or above the replication layer in some sense, because we're customizing for the workload and we're trying to make the experience as seamless as possible. That's the new interesting computer science bits that we have to invent or that we have to optimize. So the way that now that I've kind of walked through the thought process of how we've, as a community, always thought about failure, how we've had to deal with it through systems-related strategies and make application-level optimizations. The thought that I'd leave the room with is that the challenging bit here is to figure out how to meet the needs of this AI workload and how to do that in a seamless way, such that the ML engineers who are running their workloads, or the data scientists and some of these other customers, right, that Ketan and others referred to, they have a seamless experience, because we don't want them to be deeply involved in the sausage making of what happens in the infrastructure layer. Did network fail, or did a machine fail, or what are the abstractions or the frameworks that are handling this level of failure, right? It's for all of us who are thinking about scale, infrastructure, and so on, to make that as seamless as possible. If we can do that well, then we've used our time well. So I would encourage people to not worry that much about the cost and the application things. Maybe you can do that, but I would think of that as the basics in our toolbox already that we need to solve. Is this higher layer of application properties that we want, and ways that we want to be able to accelerate these data scientists and ML engineers who are exploring new models and running things on our infra that we should focus more of our time and attention on.
Yep, totally agree. Thank you for the fantastic answer, KV. I want to be mindful of the time. We're almost running out of time, but I do want to have Susan chip in on a question for you. The question for you, Susan, is what are the limitations? What limitations exist to challenge larger scale language model even further? Are we at the tipping point for how large this model can get?
Yeah, thanks for asking this question. So from my perspective, I guess, kind of extending upon all the existing answers about compute and data, really the limitations for building these large language models is a function of how large a compute cluster can get. So the size of this fully interconnected compute cluster is a bounding factor, but also the availability and uptime, right? So this goes back to the failures that KB was talking about. But fundamentally, we still rely on like synchronous gradient descent, mostly for stability reasons, but this could potentially be relaxed, but it's also unclear if there's like convergence implications where the model can just sort of degrade over time if we do that. So, if you think about if there's like a 0.01% failure rate per hour per GPU, that quickly grows to like 70% failure rate if you get to 12,000 GPUs. So this geometric distribution is relentless. And so as we're scaling, we're already seeing kind of this coming up as in our workloads. And the flip side of all this is the feasibility deployment, right? If you train all these models that are this large, if you want to actually apply them in any kind of practical use case, there's latency requirements there, which may not necessarily be the largest model that you can develop for research. So, also in this space, you see models scaling up, many orders of magnitude larger than really feasible to be deployed. So that's an issue that we're already facing right now. On the data side, though, as we're building these like large foundational models, it's also not quite clear what the composition or quality of data needs to be to develop these models that can perform well on like variety of tasks that you're training these models for. So it's really tough to balance between overfitting to the training set versus the ability to learn any kind of underlying structure from seeing the same pattern in the data set repeatedly. And also in the world where like content becomes all AI generated, in the future, presumably, potentially, the data sources that we use to feed into these models can also grow to be contaminated or amplifying existing model or biases in models, right? So quantifying and measuring this kind of drift is going to be an ongoing challenge.
Great. Thank you. Thank you, Susan, for that. So we are at time. I would like to thank all the speakers for their great talks and their time for the Q&A session. We will take a short break and then come back at, I think, 11:40 for the second half of the talks. Hopefully see everybody in a few minutes.